I'm so glad you found your way here to this quiet corner of the cosmos, where science speaks in whispers and the universe unfolds like a bedtime story written in starlight. Tonight, we're embarking on a luminous journey through the vast darkness of space, following photons as they dance across billions of years and trillions of miles to reach your eyes. We'll discover how light travels, why it behaves the way it does, and what secrets it carries from the deepest reaches of the universe. It's a tale of electromagnetic waves, cosmic messengers, and the delicate threads that connect us to every star in the night sky. Before we drift into this gentle exploration, I'd love to know where in the world you're listening from tonight, and what time it is in your corner of the universe. There's something beautifully poetic about the fact that while you're here, perhaps preparing for sleep, the light from distant stars is still traveling toward us, carrying stories from when the universe was young. Drop a comment below and let me know your celestial coordinates. If this peaceful voyage through space appeals to you, I'd be ever so grateful if you gave this video a gentle thumbs up, and perhaps consider subscribing to join our community of sleepy stargazers. It helps other curious minds find their way to these quiet cosmic conversations. Now, I do hope tonight's journey isn't so fascinating that it keeps you awake. But if it does, well, at least you'll drift off knowing a bit more about the fundamental force that illuminates everything we see. So settle in, let your breathing slow, and prepare to follow light itself on its extraordinary journey through the cosmos. Light is perhaps the most familiar yet mysterious phenomenon in our universe. It warms your face on a summer morning, carries the twinkle of distant stars to your eyes, and right now, it's bouncing off these words to help you read them. Yet for something so fundamental to our existence, light behaves in ways that seem to defy common sense. Let's begin with what might sound like a simple question, but has puzzled humanity for millennia. What exactly is light? The ancient Greeks thought vision worked by beams shooting out from our eyes, like cosmic flashlights illuminating the world. It's a charming idea, really, though it does make you wonder how they explained closing your eyes or looking at the sun without setting everything ablaze. For centuries, scholars debated whether light was made of particles or waves. Sir Isaac Newton, he of the apple and the elegant mathematics, believed light consisted of tiny particles he called corpuscles. These invisible bullets of illumination would travel in straight lines, bouncing off surfaces and explaining reflections quite nicely. It was a tidy, mechanical explanation that fit well with his clockwork universe. But then along came scientists like Thomas Young and his famous double-slit experiment in the early 1800s. When Young shone light through two narrow slits onto a screen, instead of seeing two bright lines as you'd expect from particles, he saw an interference pattern, bands of light and dark that could only be explained if light behaved like waves rippling through some invisible medium. This wave nature of light seemed to solve many puzzles. Waves could bend around corners, interfere with each other, and change direction when passing through different materials. The scientific community gradually embraced the idea that light was indeed a wave, rippling through a mysterious substance called the luminiferous ether that supposedly filled all of space. But the universe, as it often does, had more surprises in store. In the early 20th century, scientists like Max Planck and Albert Einstein discovered that light also behaves like particles in certain situations. Einstein's work on the photoelectric effect showed that light comes in discrete packets of energy called photons. Suddenly, light was both a wave and a particle, depending on how you looked at it. This wave-particle duality, as it's known, isn't just a quirk of light. It's a fundamental feature of quantum mechanics that applies to all matter and energy at the smallest scales. Light doesn't choose to be a wave or a particle. It simply is what it is, and our human concepts of waves and particles are just approximations, useful metaphors for something far more subtle and strange. Today, we understand light as electromagnetic radiation, waves of electric and magnetic fields that dance together as they propagate through space. These fields exist perpendicular to each other and to the direction of travel, like invisible ribbons fluttering in a cosmic breeze. And here's something wonderful. They need no medium to travel through. Unlike sound waves, which require air or water to carry them, light waves create their own path through the vacuum of space. The electromagnetic spectrum stretches far beyond what our eyes can see. Visible light, that narrow band of colors from violet to red, is just a tiny slice of a vast continuum that includes radio waves, microwaves, infrared radiation, ultraviolet light, X-rays, and gamma rays. They're all the same fundamental phenomenon, electromagnetic radiation, differing only in their wavelength and frequency. Think of it like a cosmic piano with keys stretching infinitely in both directions. Our eyes can only perceive a few octaves in the middle, but the entire keyboard is there, playing its electromagnetic symphony throughout the universe. Radio telescopes listen to the low, deep notes, while X-ray detectors catch the high, energetic frequencies that tell stories of black holes and stellar explosions. What makes light so special isn't just its dual nature or its vast spectrum. It's the speed at which it travels. Approximately 299,792,458 meters per second in vacuum. A number so fundamental to physics that we've defined the meter itself in terms of how far light travels in a specific fraction of a second. This speed limit isn't arbitrary. It's woven into the very fabric of space-time itself. Nothing with mass can reach the speed of light, no matter how much energy you give it. As you approach light speed, strange things happen. Time dilates, lengths contract, and your mass would approach infinity. Light itself can only travel at this cosmic speed limit because photons are massless. They're pure energy, disturbances in the electromagnetic field that must always move at the universe's ultimate speed. This speed limit has profound consequences for our understanding of the cosmos. 3 seconds ago, the sun appears as it was 8 minutes ago. The nearest star system, Alpha Centauri, shows itself as it existed over 4 years in the past. And those distant galaxies captured by the Hubble Space Telescope? Their light has been traveling for billions of years, showing us the universe as it was when it was young. In essence, astronomy is archaeology. Every photon that reaches our eyes or our telescopes is a messenger from the past, carrying information about the conditions that existed when and where it was emitted. Light doesn't just illuminate the present, it's our time machine, our connection to the cosmic past, and our only direct link to the stars. But light's journey through space isn't always straightforward. As photons travel across the vast distances between stars and galaxies, they encounter obstacles, influences, and phenomena that can alter their paths in fascinating ways. Space, despite its name, isn't truly empty. Even in the most perfect vacuum we can imagine, there are still occasional atoms of hydrogen, particles of dust, and fields of magnetic force. While these might seem negligible over the vast scales of interstellar and intergalactic space, they can have measurable effects on traveling light. Interstellar dust, composed of tiny grains of carbon, silicon, and other elements forged in stellar cores, acts like a cosmic fog. These microscopic particles, each smaller than the wavelength of visible light, scatter and absorb photons as they pass by. Blue light, with its shorter wavelength, is scattered more readily than red light, which is why distant stars often appear redder than they actually are. It's the same phenomenon that makes our sun look red at sunset, when its light must travel through more of Earth's atmosphere to reach us. This interstellar reddening can make astronomers' work challenging, like trying to determine the true color of a lamp when looking through tinted glass. But it also tells us something beautiful about the space between stars. That dust isn't just an obstruction, it's the raw material for future worlds. Those tiny grains will eventually coalesce into asteroids, planets, and perhaps the building blocks of life itself. Magnetic fields, invisible rivers of force that flow through space, can also influence light, though in more subtle ways. While ordinary light passes through magnetic fields largely unaffected, certain types of polarized light can be rotated by these cosmic magnetic highways. By studying this rotation, called Faraday rotation, astronomers can map the magnetic fields that thread through our galaxy and beyond. Gravity, that most familiar of forces, has perhaps the most dramatic effect on light's journey through space. Einstein's general relativity revealed that massive objects don't just attract matter, they curve the very fabric of space-time itself. Light, always taking the straightest possible path, follows these curves like a marble rolling along a bent surface. This gravitational lensing can magnify distant galaxies, stretch them into arcs, or even create multiple images of the same object. Galaxy clusters, containing trillions of stars worth of mass, act like cosmic magnifying glasses, allowing us to see galaxies that would otherwise be too faint and distant to detect. It's as if the universe has provided us with natural telescopes, scattered throughout space and waiting to be discovered. Sometimes, gravitational lensing creates perfect rings of light called Einstein rings, where a foreground galaxy exactly aligns with a background one, creating a halo of amplified starlight. These ethereal circles, predicted by Einstein's equations decades before they were observed, serve as stunning confirmations of general relativity and beautiful reminders of the geometric elegance underlying cosmic phenomena. But perhaps the most profound effect on light traveling through space is the expansion of the universe itself. As space stretches, carrying galaxies away from each other, the light traveling through that space gets stretched too. This cosmic expansion shifts the wavelength of photons toward the red end of the spectrum, an effect called cosmological redshift. The farther away a galaxy is, the faster it's receding from us due to cosmic expansion, and the more its light is redshifted. This relationship, first discovered by Edwin Hubble in the 1920s, not only revealed that the universe is expanding, but also gave us a way to measure cosmic distances. By analyzing how much a galaxy's light has been redshifted, we can determine how long that light has been traveling, and therefore, how far away the galaxy is. This stretching of light has a poetic quality to it. Every photon that reaches us from the distant universe has been gently pulled and elongated by the expansion of space itself. The light carries within it the story of cosmic growth, a record of how much the universe has expanded since that photon began its journey. In a very real sense, distant starlight is older and more tired than nearby starlight, having been stretched and reddened by its long voyage through expanding space. The most distant galaxies we can observe have their light stretched so much that ultraviolet radiation emitted by young, hot stars has been shifted all the way into the infrared. This is why space telescopes like the James Webb Space Telescope, designed to see an infrared light, can peer further back in cosmic time than optical telescopes. They're not just looking at different types of light. They're looking at ancient light, that has been transformed by its journey through billions of years of cosmic expansion. As light travels through the cosmos, it doesn't just carry energy from one place to another. It carries information, stories written in the language of wavelength and intensity. Every photon is a messenger, and learning to read these messages has been one of humanity's greatest intellectual achievements. The story begins with spectroscopy, the art and science of splitting light into its component colors. When you see a rainbow after a thunderstorm, you're witnessing natural spectroscopy as water droplets in the air separate sunlight into its constituent wavelengths. But scientists can do this with far greater precision, revealing secrets hidden within starlight that would otherwise remain forever mysterious. Every element in the universe has its own unique spectral fingerprint. When atoms absorb or emit light, they do so only at very specific wavelengths, creating patterns of bright and dark lines that are as distinctive as human fingerprints. Hydrogen, the most abundant element in the universe, creates a series of lines at precise wavelengths that appear the same whether we're looking at a laboratory sample or the atmosphere of a star thousands of light years away. This universality is profound. The hydrogen in your body follows exactly the same quantum mechanical rules as the hydrogen burning in the core of distant stars. The iron in your blood produces the same spectral signature as the iron forged in stellar cores billions of years ago. Light carries this information across the vast gulf of space, allowing us to perform chemical analysis on objects we'll never visit or touch. Through spectroscopy, we've learned that stars are not just points of light, but complex, dynamic objects with temperatures, compositions, and life cycles. We can determine whether a star is young or old, whether it's moving toward us or away from us, and what elements are present in its atmosphere. We can even detect planets orbiting other stars by watching for the tiny spectral shifts that occur when these worlds transit in front of their host stars. The Doppler effect, familiar to anyone who has heard the changing pitch of a passing ambulance siren, also affects light. Stars moving toward us have their light slightly blue-shifted to shorter wavelengths, while stars moving away are red-shifted to longer wavelengths. This allows astronomers to measure stellar velocities with remarkable precision, mapping the rotation of galaxies and the orbital motion of binary star systems. But light carries even more subtle information. The polarization of light, the orientation of its electromagnetic oscillations, can tell us about magnetic fields in stellar atmospheres, the alignment of dust grains in interstellar space, and the geometry of cosmic phenomena. Some light from distant galaxies is polarized in ways that suggest it has passed through regions of intense magnetic activity or has been scattered by aligned particles in the interstellar medium. Temperature information is perhaps the most direct message that light carries. Every object with a temperature above absolute zero emits thermal radiation, and the color and intensity of this radiation depends on the object's temperature. Hot, young stars appear blue-white, while cooler, older stars glow red. By measuring the color of starlight, astronomers can determine stellar temperatures with remarkable accuracy. The cosmic microwave background, the afterglow of the Big Bang itself, carries information about the universe when it was only 380,000 years old. This ancient light, now stretched by cosmic expansion into microwave wavelengths, shows us tiny temperature fluctuations from the early universe that eventually grew into the galaxies and galaxy clusters we see today. It's the oldest light we can observe, a direct message from the cosmic dawn. Even the absence of light carries information. Dark nebulae, clouds of dust and gas that block background starlight, appear as dark patches against the starry sky. These cosmic shadows tell us about the distribution of matter in space and the birthplaces of future stars. The famous Horsehead Nebula and the Coalsack are examples of these dark messengers, visible not by their own light, but by the light they prevent us from seeing. Variable stars, whose brightness changes over time, send us information about stellar pulsations, eclipses by companion stars, and explosive events. Cepheid variable stars, whose brightness cycles are directly related to their intrinsic luminosity, serve as cosmic lighthouses, allowing us to measure distances to nearby galaxies with unprecedented accuracy. Perhaps most remarkably, light can carry information about events that happened billions of years ago and billions of light years away. When massive stars explode as supernovae, they briefly outshine entire galaxies, and their light carries detailed information about the explosion mechanism, the elements created in the blast, and the expansion of the shock wave into surrounding space. Some of this light has been traveling since before our solar system existed, finally reaching us to tell the story of stellar death and cosmic enrichment. Gravitational waves, ripples in space-time itself, were first detected indirectly through their effect on light. The Laser Interferometer Gravitational Wave Observatory, LIGO, uses laser light to measure incredibly tiny changes in distance caused by passing gravitational waves. 3 billion years ago, the gravitational waves from that cosmic catastrophe eventually reached Earth, stretching and compressing space itself by less than 1/10,000th the width of a proton. Light, with its exquisite sensitivity to distance, detected this whisper from the depths of space and time. In essence, every telescope is a time machine, and every photograph of space is a historical document. The light reaching us tonight left its sources at different times throughout cosmic history, creating a layered view of the universe's past. Nearby stars show us the recent past. Distant galaxies reveal the universe's adolescence, and the cosmic microwave background carries messages from the universe's infancy. The journey of light through space is also a story of obstacles overcome and challenges met. While space is vast and mostly empty, it's not a perfect vacuum, and the interactions between light and matter along the way create some of the most beautiful and scientifically valuable phenomena in astronomy. When light encounters gas clouds in space, several things can happen, each telling us something different about the cosmic environment. If the gas is hot and energetic, perhaps heated by nearby stars or shocked by stellar winds, it can emit its own light at characteristic wavelengths. These emission nebulae glow with the colors of their constituent elements. Hydrogen glows red, oxygen shines green and blue, and nitrogen adds hints of deep red. The result is cosmic art painted in the palette of the periodic table. The Orion Nebula, visible to the naked eye as a fuzzy patch in the constellation Orion, is one of the most spectacular examples of an emission nebula. Hot, young stars at its center pump ultraviolet radiation into the surrounding gas, causing it to fluoresce like a cosmic neon sign. The nebula's complex structure, revealed in stunning detail by modern telescopes, shows shock fronts, stellar winds, and the ongoing process of star formation, all illuminated by the very stars being born within it. Reflection nebulae tell a different story. When starlight encounters dust clouds, the tiny particles scatter the light, preferentially scattering blue wavelengths more than red ones. This is the same process that makes Earth's sky blue, but in space it creates ghostly blue clouds surrounding stars. The Pleiades star cluster, the Seven Sisters of mythology, is surrounded by reflection nebulae that give the entire region an ethereal, dreamlike quality. Dark nebulae, as we mentioned earlier, block background starlight entirely, appearing as dark patches or intricate filaments against the stellar backdrop. The Horsehead Nebula in Orion is perhaps the most famous example. Its distinctive silhouette created by a dense cloud of dust and gas blocking the light from a bright emission nebula behind it. These dark clouds are often stellar nurseries, where gravity is slowly gathering material that will eventually collapse to form new stars. Planetary nebulae, despite their name, have nothing to do with planets. These beautiful, often symmetrical structures are created when dying stars shed their outer layers, creating expanding shells of gas that glow in the ultraviolet radiation from the hot, dense stellar core left behind. The Ring Nebula in Lyra and the Cat's Eye. Nebula in Draco are famous examples, showing the complex interplay between stellar evolution and the interstellar medium. Supernova remnants represent the most violent interactions between light, matter, and energy in the universe. When massive stars explode, they blast their outer layers into space at speeds of thousands of kilometers per second. These expanding shock waves heat the surrounding interstellar medium to millions of degrees, creating glowing shells of plasma that can remain visible for thousands of years. The Crab Nebula, the remnant of a supernova observed by Chinese astronomers in 1054 CE, still glows today, powered by a rapidly spinning neutron star at its center. But light's interactions with matter aren't always destructive or dramatic. Sometimes they're surprisingly gentle and beautiful. When light passes through regions of space with different densities or temperatures, it can be refracted, creating cosmic mirages. Strong gravitational fields can bend light rays, creating multiple images of the same distant object or stretching galaxies into luminous arcs. The solar corona, the sun's outer atmosphere, is normally invisible to us because it's much fainter than the bright solar disk. But during a total solar eclipse, when the moon blocks the sun's surface, the corona becomes visible as a delicate, shimmering halo of light. This ethereal glow is sunlight scattered by the extremely hot, tenuous gas of the corona, revealing structures shaped by the sun's complex magnetic field. Zodiacal light, a faint, triangular glow visible in the sky just after sunset or before sunrise, is caused by sunlight scattered by dust particles in the plane of the solar system. This interplanetary dust, remnants of comets and asteroid collisions, creates a ghostly pyramid of light that extends up from the horizon. From space, this dust disk is more prominent, and spacecraft have captured beautiful images of our solar system's dusty architecture, illuminated by scattered sunlight. Even the aurora, those dancing curtains of light in polar skies, represent light's interaction with matter, though in this case, the matter is Earth's own atmosphere. When charged particles from the solar wind collide with oxygen and nitrogen atoms in our upper atmosphere, they excite these atoms, causing them to emit light at characteristic wavelengths. Oxygen produces the familiar green glow of many auroras, while nitrogen contributes blues and purples to the celestial display. Throughout all these interactions, light remains fundamentally unchanged in its deepest nature. Individual photons may be absorbed and re-emitted, scattered in new directions, or shifted to different wavelengths, but the underlying physics remains constant. The same electromagnetic radiation that illuminates nebulae also carries radio signals, heats planets, and enables photosynthesis. Light is both the messenger and the message, the medium and the content of cosmic communication. As we follow light on its journey through space, we begin to appreciate not just its physical properties, but its role as the fundamental link between all things in the universe. Every star, every planet, Every grain of dust is connected to every other through the exchange of photons. Light doesn't just travel through space, it defines space, carrying energy and information that shapes the cosmic web of matter and energy. In the quiet darkness of space, far from the warm glow of stars, light continues its patient journey. Some photons have been traveling for billions of years, carrying messages from the early universe that we're only now beginning to receive and decode. Others were emitted just moments ago from nearby objects, racing toward Earth at the cosmic speed limit. And right now, as you listen to these words, light from your screen or the room around you is bouncing off your face, carrying information about this moment into the wider universe. Some of that light will escape Earth's atmosphere and begin its own journey through interstellar space, perhaps eventually reaching distant worlds where other beings might wonder about the nature of light and its role in connecting all things across the cosmic dark. This is the wonder of light's journey through space. It's not just a physical phenomenon, but a cosmic story of connection, information, and beauty. Every photon is a thread in the vast tapestry of the universe, weaving together past and present, near and far, the seen and the unseen. And as we learn to read the messages carried by starlight, we discover that we're not just observers of the cosmos, but participants in its grand, luminous conversation. So tonight, as you drift toward sleep, remember that you're surrounded by light from across the universe. Ancient photons from distant galaxies are gently touching your skin, carrying stories from when the cosmos was young. The light from our own sun, just 8 minutes old when it reaches us, connects us to the nuclear furnace that makes life on Earth possible. And somewhere in the darkness between the stars, new light is being born, beginning journeys that may last longer than our entire solar system will exist. Light travels through space not as a conqueror, but as a gentle messenger, carrying information and energy across the vast cosmic distances that separate all things. In its patient journey through the darkness, light reminds us that nothing in the universe is truly isolated. We are all connected by starlight, all participants in the ancient dance of photons that has been unfolding since the first stars ignited in the cosmic dawn. Sleep well, fellow traveler, knowing that you carry within you atoms forged in stellar cores, illuminated by light that has journeyed across space and time to reach this moment. The universe is vast and dark, but it's also filled with light, and that light connects us all in ways both profound and beautiful. And so we arrive at a moment of quiet transition, where the story of light itself shifts from ancient history to present mystery. We've witnessed photons racing across the cosmic void, carrying messages from distant stars and long-dead civilizations. We've seen how light bends around massive objects, how it scatters through interstellar dust, and how it reveals the very structure of space and time. But now, as we settle deeper into this celestial journey, it's time to explore something even more fundamental: how light behaves when it encounters the peculiar realm of quantum mechanics. You see, light has always been a bit of a shapeshifter. For centuries, scientists debated whether it was a wave rippling through space or a stream of particles zipping from place to place. The truth, as it often is in physics, turned out to be beautifully strange. Light is both and neither, depending on how you choose to look at it. This dual nature becomes especially important when we venture into the quantum world, where common sense takes a holiday and the universe reveals its most enchanting secrets. At the quantum level, individual photons begin to behave in ways that would make even the most imaginative storyteller pause. A single photon, can apparently travel multiple paths simultaneously, interfering with itself in patterns that suggest it somehow knows about routes it didn't take. When we try to measure which path it actually chose, the very act of observation changes its behavior, as if the universe is playing an elaborate game of hide and seek with anyone curious enough to peek behind the curtain. This quantum strangeness isn't just theoretical playground material. It has profound implications for how light travels through space and interacts with matter. In the vast emptiness between galaxies, photons exist in what physicists call superposition states, neither fully here nor there until something forces them to choose. They can become entangled with other particles, creating invisible connections that span cosmic distances faster than light itself could travel between them. Consider the cosmic microwave background radiation, that ancient afterglow of the Big Bang we discussed earlier. Each photon in that primordial light has been traveling for nearly 14 billion years, carrying with it quantum information about the early universe. Some of these photons have passed through regions where space itself is curved by massive objects, their quantum states subtly altered by gravitational fields in ways that encode information about the matter they encountered along their journey. When astronomers study distant galaxies through gravitational lensing, they're not just seeing magnified images. They're observing quantum interference patterns written in starlight, where photons that took different paths around a massive galaxy cluster can interfere with each other to create brightness variations that reveal details about both the lensing galaxy and the distant source. It's as if the universe uses quantum mechanics as a kind of cosmic calligraphy, writing stories in light that we're only beginning to learn how to read. The quantum nature of light also helps explain some of the more mysterious phenomena we observe in space. Pulsars, those rapidly spinning neutron stars, emit beams of light with quantum properties that remain coherent across vast distances. The polarization patterns in their emissions carry quantum signatures that tell us about the extreme magnetic fields surrounding these collapsed stars. Similarly, the light from active galactic nuclei shows quantum correlations that persist despite the chaotic environments from which they emerge. Perhaps most remarkably, quantum mechanics suggests that empty space itself is never truly empty. Even in the perfect vacuum between galaxies, virtual photons constantly pop into existence and disappear again, creating a quantum foam of electromagnetic activity. This isn't just abstract theory. These virtual photons can have real effects, subtly altering the paths of real photons traveling through seemingly empty space and contributing to phenomena like the cosmological redshift that reveals the expansion of the universe. There's also the fascinating question of quantum decoherence on cosmic scales. As photons travel through space, they interact with this quantum foam, with magnetic fields, with gravitational waves, and with the occasional particle of interstellar medium. Each interaction threatens to destroy the delicate quantum superpositions that the photons might have carried from their source. Yet somehow, some quantum information survives these billion-year journeys, arriving at our telescopes with stories of distant worlds still encoded in their quantum states. This has led some physicists to propose that space itself might be a kind of quantum information storage medium, where the history of every photon's journey leaves subtle traces in the fabric of spacetime. If true, this would mean that the universe is not just expanding and evolving, but also remembering, accumulating quantum memories in the very structure of space itself. The implications extend beyond pure physics into the realm of astrobiology and the search for extraterrestrial intelligence. If advanced civilizations exist elsewhere in the universe, They might have learned to manipulate the quantum properties of light for communication purposes. Quantum entanglement could, in principle, allow for instantaneous communication across any distance, though the practical challenges remain formidable. More realistically, alien civilizations might encode information in the quantum states of the light they emit, creating signatures that would be invisible to classical astronomy, but detectable to quantum-sensitive instruments. We're beginning to develop such instruments here on Earth. Quantum telescopes that can detect individual photons and measure their quantum properties are opening new windows into the cosmos. These devices can potentially reveal information about distant objects that classical telescopes miss entirely, detecting quantum correlations in starlight that encode details about stellar magnetic fields, planetary atmospheres, and even potentially biological processes. The quantum realm also offers new perspectives on some of cosmology's biggest puzzles. Dark energy, the mysterious force driving the acceleration of cosmic expansion, might be related to the quantum properties of empty space. Some theories suggest that the quantum vacuum itself has energy, and that changes in this vacuum energy as the universe expands could explain why galaxies are flying apart ever faster. Similarly, dark matter might interact with ordinary matter primarily through quantum mechanical processes that we haven't yet learned to detect. If dark matter particles can become quantum entangled with photons, they might leave subtle signatures in the cosmic microwave background or in the light from distant stars, signatures that we're only now developing the theoretical framework to understand. As we drift deeper into this quantum wonderland, it's worth remembering that we're not just passive observers of these phenomena. Every time we point a telescope at the sky and detect a photon, we're participating in a quantum measurement that collapses probability waves and actualizes one specific outcome from a vast range of possibilities. In a very real sense, the act of astronomical observation helps to create the reality we observe, bringing distant quantum possibilities into concrete existence through the simple act of looking. This participatory aspect of quantum mechanics adds a poetic dimension to our cosmic journey. We are not separate from the universe we study. We are quantum beings made of quantum particles, observing quantum light from quantum sources, all embedded in a quantum space-time that connects everything to everything else through invisible threads of possibility and correlation. So as photons from distant galaxies rain down upon us carrying their quantum stories, we become part of those stories. Each measurement we make, each observation we record, each moment of wonder we experience while contemplating the night sky becomes woven into the quantum fabric of cosmic history. We are not just studying the universe, we are helping to write its ongoing story, one quantum interaction at a time. The light that began its journey billions of years ago in some distant stellar furnace carries within its quantum essence not just information about its origin, but also the potential for all the interactions it might have along its journey to us. When it finally reaches our eyes or our instruments, that potential collapses into reality, and we become co-authors of a cosmic narrative that stretches from the quantum realm to the largest scales of space and time. In this quantum dance of light and observation, every photon is both messenger and message, every observation both question and answer, every moment of cosmic contemplation both ending and beginning. Now we arrive at the intersection of mystery and mechanism, where light carries not just brightness, but information itself. For 13.8 billion years, every photon that has traveled through space has been gathering data, collecting stories, accumulating the secrets of the cosmos in ways both subtle and profound. Light, you see, is the universe's original data storage system. Each photon that reaches us carries within it a compressed history of everything it has encountered on its journey. The starlight touching your window tonight began its voyage in the nuclear furnace of a distant sun, carrying with it the signature of that star's composition, its temperature, its age, and its motion through space. But that's only the beginning of the story. As light travels through the vast emptiness between stars, it doesn't remain unchanged. It interacts with cosmic dust, bends around massive objects, gets stretched by the expansion of space itself, and occasionally encounters magnetic fields that twist its polarization. Each of these interactions leaves a fingerprint, a subtle alteration that astronomers have learned to read like pages in a cosmic library. Consider the phenomenon of redshift, one of light's most eloquent testimonies. When light travels from distant galaxies, the expansion of the universe stretches its wavelengths, shifting them toward the red end of the spectrum. The more distant the galaxy, the greater the redshift. This isn't just a curiosity, it's a direct measurement of cosmic history. That redshifted light tells us not only how far away a galaxy is, but how long ago we're seeing it, allowing us to peer back through time and watch the universe evolve. But light carries even more sophisticated information through spectroscopy, the art of splitting light into its component colors. When light passes through or is emitted by matter, specific wavelengths are absorbed or enhanced, creating a unique spectral fingerprint. Every element, every molecule, every type of atom has its own signature pattern of lines in the spectrum. By analyzing these patterns, we can determine what distant stars and galaxies are made of, even though they're separated from us by distances so vast that physical travel would take millions of lifetimes. This technique has revealed one of the most startling discoveries in modern astronomy. The universe is not made primarily of the familiar matter we know. Normal matter, the stuff of stars and planets and people, comprises only about 5% of the universe. The rest is divided between dark matter, which reveals itself through gravitational effects, and dark energy, which drives the accelerating expansion of space itself. Light helped us discover our cosmic insignificance in the most beautiful way possible. Light also carries information about time itself through gravitational lensing. When light passes near massive objects like galaxies or black holes, the curvature of space-time bends the light's path, acting like a cosmic magnifying glass. This effect not only allows us to see objects that would otherwise be hidden behind massive structures, but it also creates multiple images of the same distant object, each taking a slightly different path through curved space-time. Sometimes we can watch the same supernova explosion happen multiple times as different light paths reach us at different moments. The cosmic microwave background radiation, that gentle afterglow of the Big Bang, carries perhaps the most ancient information of all. This light has been traveling for nearly 14 billion years, carrying with it the imprint of the earliest structures in the universe. Tiny fluctuations in this background radiation, variations of mere millionths of a degree, reveal the seeds that would eventually grow into galaxies, stars, and everything we see today. Even more remarkably, light carries quantum information. Quantum entanglement, that spooky action at a distance that Einstein found so troubling, can be preserved across vast distances through photons. This means that light doesn't just carry classical information about brightness and color, but can also carry quantum states that remain mysteriously correlated across space and time. The polarization of light tells us about magnetic fields in space, regions where charged particles spiral and dance in ways invisible to our eyes, but clearly written in the twist of electromagnetic waves. Pulsar signals, Those lighthouse beams from rotating neutron stars carry information about some of the most extreme conditions in the universe, where matter is compressed to densities greater than atomic nuclei and magnetic fields are trillions of times stronger than Earth's. Light even carries information about its own journey through the phenomenon of scintillation. Just as stars twinkle due to Earth's atmosphere, light from distant sources can twinkle as it passes through the interstellar medium, revealing the density and turbulence of gas clouds scattered throughout the galaxy. Perhaps most poetically, light carries the information of existence itself. Every photon that reaches us is proof that something, somewhere, once shone. The light from stars that died before Earth formed still travels through space, carrying the last testament of stellar lives that ended eons ago. In this sense, light is not just information, it's memory, preserving the stories of cosmic events long after their sources have vanished. And in our modern age, we've learned to read these messages with increasing sophistication. Space telescopes scan the sky in wavelengths invisible to human eyes, from radio waves to gamma rays, each revealing different aspects of cosmic phenomena. We've built interferometers that combine light from multiple telescopes to achieve resolution finer than anything a single instrument could provide. We've created detectors sensitive enough to catch individual photons that have traveled across the entire observable universe. The information carried by light has revealed that we live in a universe far stranger and more wonderful than our ancestors ever imagined. It's shown us black holes where time stops, neutron stars where a teaspoon of matter weighs as much as a mountain, and galaxies so distant that we see them as they were when the universe was young. Light has taught us that space and time are woven together, that matter and energy are interchangeable, and that the universe itself had a beginning and continues to evolve. As you rest tonight, remember that you are bathed in information. Light from the sun, reflected from the moon, emitted by distant stars, and even the faint glow of the cosmic microwave background, all carry their messages to you. Each photon is a tiny ambassador from somewhere else in the cosmos, bringing news of distant worlds and ancient events. Looking at your cosmic journey through light and space, we've explored how photons carry the universe's deepest secrets across billions of years. Now, as we continue our gentle drift through the cosmos, let's turn our attention to something equally mysterious, yet intimately familiar. The quantum realm, where light reveals its most peculiar nature. You might think that after traveling billions of light years through space, we'd have light figured out completely. But here's where our story takes a delightfully strange turn. Light, for all its cosmic grandeur, still holds secrets that would make even the most seasoned astronomers scratch their heads and reach for another cup of tea. We've seen how light acts as the universe's faithful messenger, carrying information about distant stars and ancient galaxies. But when we zoom in, when we look at light not as waves washing across space, but as individual particles called photons, something wonderfully weird happens. Light starts behaving like it's following rules from a dream rather than a physics textbook. Picture this. You're holding a single photon, if such a thing were possible, which it isn't. But let's imagine anyway. This tiny packet of light energy doesn't know quite what it wants to be. Is it a wave, rippling through space like a gentle disturbance on a cosmic pond? Or is it a particle, a discrete little bullet of energy zipping from here to there? The answer, rather cheekily, is both, and neither. And it depends entirely on whether anyone is watching. This is the heart of quantum mechanics as it applies to light, and it's called wave-particle duality. When no one is looking, when no measurement is being made, light spreads out like a wave, existing in multiple states simultaneously. It can be in several places at once, taking all possible paths through space like a photon, having an existential crisis about which route to choose. But the moment you try to pin it down, the moment you set up an experiment to catch light in the act, it snaps into focus as a particle. It picks one path, one location, one definite state. It's as if light is perpetually playing an elaborate game of cosmic hide-and-seek, shape-shifting depending on who's seeking. This isn't just theoretical whimsy. Scientists have demonstrated this repeatedly through experiments like the famous double-slit experiment. When you shine light through two parallel slits, it creates an interference pattern on the other side, clear evidence that light is behaving as a wave, going through both slits simultaneously and interfering with itself. But if you place a detector to see which slit each photon goes through, the wave pattern disappears. The light suddenly behaves like particles, each one choosing a single slit. It's as if the universe has a sense of humor about observation itself. The very act of trying to understand light changes its behavior. There's something almost philosophical about this, isn't there? The observer and the observed are not separate entities, but part of a single, interconnected dance. This quantum strangeness extends beyond simple wave-particle duality. Light exhibits what Einstein famously called spooky action at a distance, quantum entanglement. Two photons can become entangled, linked in such a way that measuring one instantly affects the other, regardless of the distance between them. You could have one photon on Earth and its entangled partner orbiting Alpha Centauri, and they would still maintain their mysterious connection. When you measure the polarization of one entangled photon and find it spinning clockwise, its distant partner will instantly be found spinning counterclockwise. Not because it received a signal. That would take over 4 years to travel from Earth to Alpha Centauri, but because they exist as a single quantum system, a unified whole that transcends our everyday notions of space and time. This quantum entanglement isn't just a curiosity for physicists with too much time on their hands. It's the foundation for emerging technologies like quantum computing and quantum cryptography. Scientists are learning to harness these strange quantum properties to create computers that could solve certain problems exponentially faster than today's machines, and communication systems that would be theoretically impossible to hack. But perhaps most intriguingly, quantum mechanics suggests that light, and indeed all matter, exists in a state of superposition until observed. This means that light can be in multiple states simultaneously. Different colors, different polarizations, different energies all at once. It's only when we interact with it, when we make a measurement, that it collapses into a single, definite state. This has led some physicists to propose that consciousness itself might play a fundamental role in shaping reality. Not in a mystical sense, but in the very real sense that the act of observation appears to be necessary for the universe to have definite properties. Without observers, the universe might exist in a perpetual state of quantum possibility, neither here nor there, neither this nor that. Of course, this raises profound questions. If a photon travels across the universe for 13 billion years in a state of quantum superposition, carrying information about ancient stars and primordial galaxies, what happens to all that cosmic history when it finally strikes your eye or hits a telescope detector? Does the entire 13 billion year journey suddenly snap into definite reality at that moment? Some interpretations of quantum mechanics suggest exactly that. The many worlds interpretation proposes that every quantum measurement causes the universe to split into multiple parallel realities, each containing a different outcome. this view, every photon that reaches Earth from distant galaxies creates countless parallel universes, each with slightly different cosmic histories. It's a dizzying thought, isn't it? That the simple act of starlight touching your retina might be constantly creating new universes, new versions of reality branching off like infinite tributaries of possibility. Every time you look up at the night sky, you might be participating in the fundamental creative process of existence itself. But even if we set aside such grand metaphysical speculations, the quantum nature of light has practical implications for how we understand the cosmos. The cosmic microwave background, that ancient afterglow of the Big Bang we discussed earlier, exists as a quantum field permeating all of space. Its tiny fluctuations, preserved from the universe's infancy, carry quantum information about the very birth of reality. When we observe this background radiation with our most sensitive instruments, we're not just seeing the universe as it was nearly 14 billion years ago. We're collapsing quantum wave functions that have been evolving since the first moments after creation. We're participating in a cosmic measurement that helps determine the very nature of space-time itself. Similarly, the light from distant quasars and supernovae carries quantum information across billions of years. Each photon is a quantum messenger, existing in superposition as it travels, carrying not just classical information about brightness and color, but quantum information about the fundamental nature of reality itself. This quantum aspect of light also affects how we understand the expansion of the universe. As space itself expands, it stretches the wavelengths of photons traveling through it, causing the redshift we use to measure cosmic distances. But this stretching happens to quantum wave functions, not just classical waves. The expansion of the universe is, in a very real sense, a quantum mechanical process affecting the probability distributions of photons across cosmic scales. Even dark energy, that mysterious force driving the accelerating expansion of the universe, might have quantum origins. Some theories propose that dark energy emerges from quantum fluctuations in empty space itself, from the ceaseless creation and annihilation of virtual particles that pop in and out of existence in the quantum vacuum. If this is true, then the fate of the universe, whether it will expand forever, collapse back on itself, or tear apart in a big rip, might ultimately be determined by quantum mechanical processes operating on scales both infinitesimally small and cosmologically vast. As you drift towards sleep tonight, consider this: the gentle light from your bedside lamp, the starlight filtering through your window, even the infrared radiation from your own warm body. All of it exists in quantum superposition until the moment it interacts with something else. You are surrounded by fields of possibility, waves of potential that collapse into definite reality only through the act of interaction. The universe, it seems, is not a collection of definite objects moving through space, but rather a vast web of quantum relationships, constantly creating itself through the act of observation and measurement. Light, our cosmic messenger, is also our guide into this strange realm where the boundary between the observer and the observed, between mind and matter, becomes beautifully, mysteriously blurred. And perhaps that's the most profound message light carries across the cosmos. Not just information about distant stars and ancient galaxies, but the deeper truth that reality itself is participatory. That consciousness and cosmos are not separate things, but part of a single, unfolding quantum story. A story in which every photon, every observation, every moment of awareness contributes to the ongoing creation of existence itself. Sweet dreams, fellow quantum traveler. Building on our journey through cosmic mysteries, we arrive at another profound phenomenon that shapes our understanding of the universe: polarization. Light doesn't just travel as waves through space. It carries with it a hidden orientation, a direction of oscillation that acts like an invisible signature written into every photon. When light waves vibrate in a particular direction, we say they are polarized. Imagine light as countless tiny springs bouncing up and down, side to side, or in any direction perpendicular to their path. Unpolarized light vibrates randomly in all these directions at once, like a crowd of people waving their arms chaotically. But when light becomes polarized, all those vibrations align, creating a more ordered, directional wave pattern. This polarization carries extraordinary information about the cosmic environments through which light has traveled. When starlight passes through the magnetic fields surrounding stars, those fields twist and align the light's polarization in specific ways. The dust grains floating between stars, themselves aligned by magnetic forces, act like cosmic polarizing filters, imprinting their signature onto passing light. What makes this particularly fascinating is that polarization reveals invisible structures in space. Magnetic fields, which we cannot see directly, leave their fingerprints in the polarized light that reaches our telescopes. These fields thread through galaxies like invisible highways, guiding the motion of charged particles and shaping the formation of stars and planetary systems. In stellar nurseries, where new stars are born from collapsing clouds of gas and dust, magnetic fields play a crucial role in controlling how matter falls inward. The polarization of light from these regions tells us about the strength and direction of these fields, helping us understand the delicate dance between gravity trying to pull material together and magnetic forces that can either help or hinder this process. Even more remarkably, the cosmic microwave background radiation, that ancient afterglow of the Big Bang we discussed earlier, carries polarization patterns that encode information about the universe's earliest moments. These patterns, incredibly faint and requiring the most sensitive instruments to detect, tell us about the primordial gravitational waves that rippled through space during cosmic inflation. That brief period of rapid expansion just after the universe began. The polarization of this ancient light acts like a fossil record of cosmic inflation, providing evidence for one of the most important theories in cosmology. When gravitational waves from inflation passed through the hot, dense plasma of the early universe, they left subtle imprints on the polarization patterns we can still observe today, billions of years later. But polarization isn't just about grand cosmic phenomena. It reveals intimate details about individual stars and their environments. When light from a star passes through its own atmosphere or through material in a binary star system, the polarization changes in ways that tell us about temperatures, densities, and the presence of magnetic fields we could never detect otherwise. Some of the most extreme objects in the universe, like neutron stars and black holes, create such intense magnetic fields that they dramatically polarize any light that escapes their vicinity. These polarization signatures help us study matter under conditions so extreme they cannot be replicated anywhere on Earth, providing laboratories for testing the fundamental laws of physics. In the atmospheres of distant planets, polarization helps us identify the composition of clouds and atmospheric particles. When sunlight reflects off these planetary atmospheres, the degree and angle of polarization tell us whether we're looking at water droplets, ice crystals, or exotic compounds in alien skies. The study of polarized light has even opened new windows into the search for life beyond Earth. Certain biological processes can create distinctive polarization patterns, and future telescopes designed to study the atmospheres of Earth-like planets around other stars will look for these subtle polarization signatures as potential indicators of biological activity. What's particularly elegant about polarization is how it connects the quantum nature of light with large-scale cosmic structures. Each photon carries not just energy and momentum, but also this property of polarization that emerges from the wave nature of electromagnetic radiation. When billions of photons from a distant star all carry similar polarization information, they collectively tell us about magnetic fields spanning light years of space. The instruments we use to study polarized light are marvels of precision engineering. They can measure polarization changes smaller than 1 part in a million, detecting the faintest whispers of magnetic fields in the depths of space. These measurements require extraordinary care, as even the slightest imperfection in a telescope mirror or the Earth's atmosphere can introduce false polarization signals. Recent advances in polarimetry, the measurement of polarized light, have revolutionized our understanding of cosmic magnetic fields. We've discovered that these fields are far more complex and important than previously thought, playing crucial roles in everything from the formation of the first stars to the evolution of entire galaxies. The interstellar medium, that thin soup of gas and dust between stars, is threaded through with magnetic fields that organize and channel the flow of material on galactic scales. Polarization measurements reveal these invisible highways, showing us how matter moves through galaxies and how magnetic fields influence the birth of new stars. As we develop more sophisticated polarization techniques, we're beginning to map the three-dimensional structure of magnetic fields throughout our galaxy and beyond. This cosmic cartography reveals a universe far more organized and interconnected than we might have imagined, with magnetic field lines stretching across vast distances and linking seemingly separate regions of space. The polarization of light also provides a unique probe of the fundamental symmetries of nature. In some exotic theories of physics, the polarization of light from distant sources might rotate as it travels through space, potentially revealing new physics beyond our current understanding. These measurements push the boundaries of precision, searching for the faintest hints of new physical laws encoded in the orientation of ancient light. Perhaps most poetically, polarization reminds us that light carries not just brightness and color, but also a hidden dimension of information about its journey through the cosmos. Every polarized photon that reaches Earth has been touched by magnetic fields, scattered by dust grains, and shaped by the environments through which it has passed, carrying within its orientation a story of cosmic forces we are only beginning to understand. Light carries more than just illumination across the cosmos. It brings quantum secrets that blur the boundary between the physical and the mysterious. While our earlier journey revealed how photons travel through space, gathering information from distant stars and galaxies, there's an even stranger story hiding in the quantum realm. Light doesn't just connect us to the universe through classical physics. It weaves us into a quantum tapestry where observation itself becomes an act of creation. When scientists first began studying light at the quantum level, they discovered something that challenged everything we thought we knew about reality. Light isn't just a wave or just a particle. It exists in what physicists call superposition, a quantum state where it embodies all possibilities simultaneously until the moment we observe it. Imagine a coin spinning in the air, neither heads nor tails, but somehow both, until it lands and reality chooses. This is the quantum world that light inhabits, a realm where the very act of looking changes what we see. This quantum strangeness isn't just laboratory curiosity. Every photon that reaches your eye from a distant star has traveled through this quantum landscape, carrying information not just about where it came from, but about the fundamental nature of reality itself. When light from the cosmic microwave background reaches our telescopes, it brings whispers of quantum fluctuations from the earliest moments of the universe, tiny variations that would eventually grow into the galaxies we see today. But perhaps the most remarkable quantum property of light is entanglement. When two photons become entangled, they form an invisible connection that transcends space and time. Measure one photon's polarization, and instantly, faster than light could travel between them, its partner will exhibit the corresponding property, no matter how far apart they are. Einstein famously called this spooky action at a distance, but today we know it's one of the most fundamental features of quantum reality. This quantum entanglement isn't just happening in carefully controlled laboratory experiments. Throughout the universe, photons are becoming entangled through interactions with matter, with magnetic fields, with the very fabric of space-time itself. Some researchers believe that the cosmic web of dark matter might be laced with quantum correlations, creating a kind of cosmic consciousness where information can flow instantaneously across vast distances. Consider what this means for the light reaching us from ancient galaxies. Those photons may carry quantum correlations with particles that stayed behind, creating invisible threads connecting us to the most distant corners of the universe. When you look up at the night sky, you're not just seeing ancient light. You might be participating in a quantum conversation that spans billions of years and countless light years. The quantum nature of light also reveals something profound about the role of consciousness in the universe. In quantum mechanics, the act of observation doesn't just reveal reality, it helps create it. When we observe light, we collapse its wave function, forcing it to choose from its superposition of possibilities. This suggests that consciousness isn't separate from the physical universe, but is intimately woven into its fabric. Some physicists have proposed that this quantum relationship between observer and observed might explain why the universe seems so perfectly tuned for the existence of conscious beings. Perhaps consciousness and cosmos evolved together, each shaping the other through countless quantum interactions. Every time you observe a photon, whether from your reading lamp or from a galaxy billions of light years away, you're participating in this cosmic dance between mind and matter. The quantum properties of light also offer tantalizing glimpses into the future of human understanding. Quantum communication, using entangled photons to transmit information, could eventually allow us to create unbreakable codes and instantaneous communication networks. Quantum computers, which manipulate the superposition states of photons and other particles, might one day solve problems that would take classical computers longer than the age of the universe. Even more remarkably, some scientists are exploring whether quantum effects in biological systems might explain consciousness itself. The human brain, with its billions of neurons and trillions of synapses, might be nature's most sophisticated quantum computer, using the strange properties of light and matter to create the rich inner world of thoughts, feelings, and experiences we call consciousness. This quantum perspective transforms our understanding of what it means to observe the universe. We're not passive recipients of cosmic information, but active participants in a quantum conversation that has been ongoing since the first photons escaped the primordial fireball of the Big Bang. Every observation, every measurement, every glance at the night sky contributes to the ongoing creation of reality. The light from distant stars doesn't just carry information about temperature, composition, and motion. It carries quantum possibilities that become actualized through our observation. We're not just studying the universe, we're helping to write its story, one photon at a time. The boundary between observer and observed, between mind and cosmos, dissolves in the quantum realm where light reveals its deepest secrets. As we continue to push the boundaries of our understanding, light remains our most faithful guide into the quantum mysteries of existence. 8 billion years of galactic birth and stellar death carries with it more than just photons dancing through the void. As we drift deeper into this sleepy exploration of starlight and shadows, we find ourselves approaching one of the most profound mysteries of the universe: how light itself becomes a bridge between the quantum realm and the cosmic stage, between the microscopic dance of particles and the grand theater of galaxies. You see, light doesn't simply travel through space like a well-behaved tourist following a predetermined route. It weaves, bends, and whispers secrets about the very nature of reality itself. Every photon that reaches your eye tonight, whether from a nearby street lamp or a distant quasar, has been shaped by its journey through the cosmos in ways that would make even the most imaginative storyteller pause in wonder. Consider for a moment the extraordinary fact that light possesses what physicists call quantum coherence. This means that under the right circumstances, photons can maintain their quantum properties across vast distances, carrying information not just about where they came from, but about the quantum states of the matter that created them. When a star collapses into a neutron star billions of light years away, the light it emits can retain quantum signatures of that violent transformation, delivering them to our telescopes like cosmic time capsules sealed with quantum precision. This quantum nature of light becomes particularly fascinating when we examine how it interacts with the fundamental structure of space-time itself. Einstein's general relativity tells us that massive objects warp the fabric of space and time, creating what we call gravitational fields. But what Einstein couldn't have fully anticipated was how these warped regions of space-time would affect light, not just as a classical wave, but as a quantum phenomenon. In the presence of extremely strong gravitational fields, such as those near black holes or neutron stars, light experiences what we call gravitational quantum effects. The photons don't simply follow curved paths through warped space-time. They can actually become entangled with the gravitational field itself. This creates a kind of cosmic quantum entanglement, where the properties of light become inextricably linked to the properties of the massive objects that bend space-time around them. Imagine, if you will, a photon born in the accretion disk of a supermassive black hole, that churning maelstrom of superheated matter spiraling toward the event horizon. As this photon escapes the black hole's gravitational well, it carries with it quantum information about the black hole's rotation, its electric charge, and even subtle details about the quantum vacuum fluctuations near the event horizon. When that photon finally reaches Earth millions of years later, it brings with it a quantum fingerprint of one of the most extreme environments in the universe. But the quantum properties of cosmic light extend far beyond individual photons. In the vast expanses between galaxies, in regions we once thought were empty vacuum, light participates in what quantum field theory describes as zero-point fluctuations. Even in the apparent emptiness of intergalactic space, the quantum vacuum is alive with virtual particles popping in and out of existence, creating and annihilating in pairs so quickly that they seem to flicker at the very edge of reality. These quantum vacuum fluctuations aren't just theoretical curiosities. They have measurable effects on light traveling through what we perceive as empty space. Over cosmic distances, these tiny quantum interactions can accumulate, subtly altering the polarization of light, introducing minute phase shifts, and even creating correlations between photons that were never directly connected. It's as if the universe has a quantum memory stored in the very fabric of space-time, and light serves as both the librarian and the reader of that cosmic information. The cosmic microwave background, that gentle afterglow of the Big Bang we discussed earlier, provides one of the most beautiful examples of quantum information preserved in light. When the universe first became transparent about 380,000 years after the Big Bang, the photons that were released didn't just carry information about the temperature and density of the early universe. They also preserved quantum correlations that had been established during the inflationary epoch, when the entire observable universe was smaller than a proton. These quantum correlations, stretched across the cosmos by the expansion of space itself, are still detectable today in the tiny temperature fluctuations of the cosmic microwave background. When we measure the polarization patterns in this ancient light, we're essentially reading a quantum message written in the first moments of the universe's existence. It's as if the cosmos left us a quantum love letter, written in the language of light and encoded in the very structure of space-time. But perhaps the most profound aspect of light's quantum nature in the cosmic context is how it connects us, quite literally, to the quantum foundations of reality. Every photon that enters your eye, whether from the sun, a distant star, or even the cosmic microwave background, has maintained its quantum properties throughout its journey. When that photon is absorbed by the rhodopsin molecules in your retina, it triggers a quantum mechanical process that begins with the photon's energy causing a single molecule to change its shape. This quantum interaction between cosmic light and the molecules in your eye is part of an unbroken chain of quantum processes that connects your consciousness to the quantum field fluctuations that occurred in the first moments after the Big Bang. In a very real sense, your awareness of the night sky is a quantum phenomenon, emerging from the same fundamental processes that created the galaxies, stars, and planets you observe. The implications of this quantum connection extend far beyond poetic metaphor. Modern quantum field theory suggests that the universe can be understood as a vast network of quantum correlations, with light serving as the primary medium through which these correlations are established and maintained. When we look at distant galaxies, we're not just seeing their light, we're participating in a cosmic quantum network that connects all luminous objects across space and time. This quantum network has profound implications for our understanding of cosmic evolution. The formation of structure in the universe, from the largest galaxy clusters to the smallest stellar systems, may be fundamentally guided by quantum correlations preserved in light. The patterns we see in the cosmic web, those vast filaments of dark matter and ordinary matter that span hundreds of millions of light years, may reflect quantum information that was encoded in the primordial light of the early universe. Recent advances in quantum astronomy are beginning to explore these connections more directly. Astronomers are now using quantum-enhanced telescopes that can detect individual photons and measure their quantum properties with unprecedented precision. These instruments can detect quantum entanglement between photons from different stars, measure the quantum coherence of light that has traveled across cosmic distances, and even search for signatures of quantum gravitational effects in the light from distant galaxies. One of the most exciting frontiers in this field is the search for what physicists call quantum signatures of cosmic inflation. According to inflationary cosmology, the rapid expansion of space in the first fraction of a second after the Big Bang should have created specific patterns of quantum correlations in the cosmic microwave background. These correlations would be a direct observational link to quantum gravity effects operating at the Planck scale, the smallest possible scale of space and time. If detected, these quantum signatures would represent the first direct observation of quantum gravitational phenomena, bridging the gap between quantum mechanics and general relativity in a way that could revolutionize our understanding of both the very small and the very large. The light that carries these signatures has been traveling to us for nearly 14 billion years, preserving quantum information from the moment when the universe itself was a quantum system. As we contemplate these profound connections between light, quantum mechanics, and cosmic evolution, we begin to see that the starlight touching your face tonight is not merely electromagnetic radiation traveling through empty space. It is a carrier of quantum information, a participant in cosmic quantum correlations, and a bridge between the quantum realm and the classical world of our everyday experience. The photons reaching your eyes have maintained their quantum properties throughout journeys that span millions or billions of years. They carry with them quantum signatures of the stellar nuclear furnaces where they were born, the interstellar medium they traversed, and the gravitational fields they encountered along the way. When these photons are absorbed by your retina and trigger the quantum processes that lead to vision, you become part of this cosmic quantum network. This realization brings us to a profound truth about the nature of observation and consciousness in the universe. The very act of observing starlight is a quantum measurement, collapsing the probability waves of countless photons into definite states and creating irreversible records in your brain. Your consciousness, in observing the cosmos, becomes an active participant in the quantum evolution of the universe itself. In quantum mechanics, the act of measurement is not passive. It fundamentally alters the system being observed. When you look at a star, you are not simply receiving information about that star. You are participating in a quantum interaction that connects your conscious awareness to the quantum processes occurring in that distant stellar furnace. Your observation becomes part of the star's quantum history, just as the star's light becomes part of your conscious experience. This participatory aspect of quantum observation suggests that consciousness and cosmos are not separate entities, but aspects of a single, interconnected quantum reality. The light that connects us to the stars also connects us to the fundamental quantum processes that underlie all physical phenomena. We are not outside observers of the universe. We are quantum participants in its ongoing evolution. And so, as you settle into sleep tonight, remember that the gentle starlight filtering through your window carries more than just photons. It carries quantum information from across the cosmos, connecting you to distant stars, ancient galaxies, and the very quantum foundations of reality itself. The universe speaks in light, and every photon carries a story. As we continue our journey through the cosmic dark, these traveling messengers begin to reveal secrets that transform our understanding of reality itself. Light doesn't merely illuminate the darkness. It becomes our guide through dimensions of existence we're only beginning to comprehend. Picture yourself floating in the depths of space, billions of years after those first stars ignited. The universe has grown vast and complex, filled with galaxies spinning like cosmic pinwheels, each one a city of billions of stars. But the light streaming between them carries far more than simple illumination. Every beam is encoded with information, quantum signatures, and traces of its extraordinary journey through space and time. When light leaves a distant star, it begins as pure energy born from nuclear fusion in stellar cores. Hydrogen atoms collide and merge under unimaginable pressure and heat, releasing photons that begin an epic voyage. But these aren't ordinary particles of light. Each photon carries within it a quantum fingerprint, a unique signature that tells the story of where it came from, what it encountered along the way, and how the universe itself has changed during its journey. As this light travels through space, it encounters the invisible architecture of the cosmos. Dark matter, that mysterious substance we cannot see or touch, bends space-time itself, creating gravitational lenses that curve the path of light like cosmic magnifying glasses. Through these natural telescopes, we can see further into the universe than should be possible, observing galaxies that would otherwise remain hidden behind closer objects. The light also passes through vast clouds of interstellar dust and gas, the raw materials from which new stars will one day be born. These encounters leave their mark. Certain wavelengths are absorbed while others pass through unchanged, creating what astronomers call absorption lines. It's like a cosmic barcode embedded in the light itself, telling us exactly which elements the light encountered on its journey. But perhaps most remarkably, the expansion of the universe itself transforms the light as it travels. Space is growing larger, stretching like a balloon being inflated, and this stretching pulls the wavelengths of light longer and longer. Blue light becomes green, green becomes red, and red shifts into infrared. This redshift, as it's called, allows us to measure not just how far away a galaxy is, but how long ago the light began its journey toward us. The further we look into space, the further back in time we see. The light from the most distant galaxies has been traveling for over 13 billion years, showing us the universe when it was young, chaotic, and very different from today. These ancient photons carry messages from cosmic childhood, when the first stars were just learning to shine and galaxies were still taking their first tentative steps toward the grand structures we see today. Yet light reveals even stranger secrets as it journeys through the quantum realm of space itself. At the deepest level, reality is not the solid, predictable place our everyday experience suggests. Space is filled with quantum fields, invisible oceans of energy that fluctuate and vibrate according to the mysterious laws of quantum mechanics. Light, being both wave and particle, dances through these fields in ways that challenge our most basic assumptions about reality. Sometimes photons become entangled with other particles, creating connections that transcend ordinary space and time. Two entangled photons can influence each other instantaneously, even when separated by vast cosmic distances. The cosmic microwave background radiation, that faint afterglow of the Big Bang that fills all of space, carries perhaps the most profound message of all. This ancient light has been traveling for nearly 14 billion years, since the moment when the universe first became transparent. It carries within it the seeds of everything that would later grow into stars, galaxies, planets, and ultimately, life itself. When we detect this radiation with our telescopes, we're literally touching the light from the moment of cosmic creation. But light doesn't just carry information from the past. It actively participates in shaping the present and future of the universe. In regions where new stars are being born, the intense radiation from hot young stars sculpts the surrounding gas clouds, creating the spectacular nebulae that grace our night sky images. These stellar nurseries glow with the light of creation itself, as gravity and radiation work together to spark new generations of stars. Even black holes, those regions of space where gravity is so strong that nothing can escape, reveal their presence through the behavior of light around them. As matter spirals into a black hole, it heats up and glows brilliantly before disappearing forever beyond the event horizon. The light from these accretion disks tells us about some of the most extreme environments in the universe, where space and time themselves become twisted beyond recognition. The polarization of light adds another layer of information to these cosmic messages. As light waves oscillate, they can be oriented in specific directions, and this polarization changes as the light passes through magnetic fields in space. By studying polarized light from distant galaxies, we can map the invisible magnetic field lines that thread through the cosmos, revealing yet another hidden aspect of the universe's architecture. Perhaps most intriguingly, light may carry information about the quantum nature of space itself. Some theories suggest that space is not smooth and continuous as it appears, but is actually made up of tiny, discrete units at the smallest scales, a kind of pixelated reality that only becomes apparent when examined with impossible precision. The subtle effects of this quantum foam might leave their signatures in light that has traveled the greatest distances, offering clues about the fundamental nature of reality itself. As we develop more sophisticated ways to analyze light, we're beginning to decode messages that were always there but previously unreadable. Machine learning algorithms can now detect patterns in cosmic light that human observers would never notice, revealing hidden structures and relationships in the universe. We're learning to read the quantum information encoded in photons, opening new windows into the deepest mysteries of existence. The light reaching us from distant galaxies also carries evidence of dark energy, the mysterious force that is accelerating the expansion of the universe. As space grows larger at an ever-increasing rate, the light from the most distant objects is stretched and reddened in specific ways that reveal this cosmic acceleration. Through careful analysis of this ancient light, we've discovered that the universe's expansion is not slowing down as expected, but speeding up, driven by something we don't yet understand. Every photon that reaches Earth is a messenger from the cosmos, carrying stories of stellar birth and death, galactic collisions and mergers, the formation of planets, and the emergence of complex chemistry. Some of these photons began their journey before our solar system existed, traveling through space for billions of years before finally reaching our telescopes. Others left nearby stars just minutes ago, bringing us news of our immediate cosmic neighborhood. The quantum properties of light also hint at deeper connections between consciousness and cosmos. The act of observation itself plays a fundamental role in quantum mechanics, with the mere act of measurement affecting the behavior of quantum systems. While we're far from understanding these connections fully, they suggest that the universe may be far more participatory than we once believed, with observers playing an active role in determining the nature of reality. As we look toward the future, new technologies promise to reveal even more secrets hidden in cosmic light. Gravitational wave detectors can now sense ripples in space-time itself, providing a new form of cosmic messenger that complements the information carried by photons. Quantum sensors may soon be able to detect individual photons that have traveled from the edge of the observable universe, carrying information about the very first moments after the Big Bang. The search for life beyond Earth also depends on reading the messages carried by light. The atmospheres of distant planets can be analyzed by studying how starlight changes as it passes through them during planetary transits. Specific combinations of gases might reveal the presence of biological processes, allowing us to detect life on worlds we'll never visit directly. The light itself becomes our ambassador to distant worlds, carrying back reports of what it encountered in alien skies. In this grand cosmic symphony, light serves as both the music and the conductor, carrying information and energy throughout the universe, while simultaneously shaping the very structures it illuminates. From the quantum foam of empty space to the vast filaments of the cosmic web, from the birth cries of newborn stars to the death songs of ancient galaxies, light weaves together the story of existence itself. And in the quiet moments when you gaze up at the night sky, remember that you are not just observing the universe, you are participating in it. The ancient light touching your eyes has traveled impossible distances and endured unimaginable journeys to reach you. Each photon carries within it the memory of cosmic evolution, the signature of stellar alchemy, and the quantum whispers of creation itself. You are not separate from this cosmic dance of light and shadow, but an integral part of it, a conscious observer in a universe that may depend on observation for its very existence. As we drift deeper into the cosmic web of understanding, our journey through space and time brings us to one of the most fundamental questions about light itself. How does it actually move through the universe? We've seen light as messenger and memory keeper, but now we must ask ourselves what space truly is between the stars, and whether it's truly empty as it appears on those clear, quiet nights when we gaze upward. The space between galaxies might look like a perfect vacuum, a pristine nothingness where light travels unimpeded, like a ship across a still, dark ocean. But the universe, as we're learning, rarely offers such simple answers. What appears empty is actually alive with invisible currents, magnetic highways, and quantum whispers that shape every photon's journey across the cosmos. Let's begin with what we call the interstellar medium, the space between stars within our own galaxy. Far from being empty, this region is filled with a thin soup of gas and dust, mostly hydrogen with traces of heavier elements scattered by long dead stars. The density is incredibly low, far thinner than the best vacuum we can create on Earth. Yet across the vast distances that light travels, even this wispy material leaves its mark. When starlight passes through these cosmic clouds, something beautiful and revealing happens. Different wavelengths of light interact differently with the dust particles, scattering blue light more than red, much like Earth's atmosphere creates our blue skies and red sunsets. This interstellar reddening tells us about the composition and density of material between us and distant stars. Every photon becomes a tiny explorer, carrying back news of its journey through these invisible landscapes. But the interstellar medium is more than just passive dust and gas. It's threaded with magnetic fields, invisible lines of force that stretch across light years, connecting star systems in ways we're only beginning to understand. These magnetic fields, though incredibly weak by terrestrial standards, create structure in space itself, channeling the flow of charged particles and influencing how cosmic rays, those high-energy messengers from distant corners of the universe, make their way to us. When we venture beyond our galaxy into intergalactic space, the medium becomes even more tenuous, yet it never truly disappears. The space between galaxies contains what astronomers call the intergalactic medium, a sparse web of gas that traces the large-scale structure of the universe. This gas, heated to millions of degrees by the gravitational energy of collapsing matter, is so hot that it glows primarily in X-rays, invisible to our eyes, but detectable to specialized telescopes. Here, in these vast cosmic voids, light encounters phenomena that challenge our everyday understanding of empty space. Gravity itself becomes a lens, bending the paths of photons as they pass near massive objects. A photon that began its journey from a distant quasar billions of years ago might have its path curved by the gravitational field of a galaxy cluster, arriving at our telescopes from a slightly different direction than it started. This gravitational lensing has become one of our most powerful tools for studying the universe, allowing us to see galaxies that would otherwise be hidden behind closer objects. Even more subtle is the expansion of space itself. As light travels across cosmic distances, the universe expands beneath it, stretching the wavelength of the photons like a note played on a guitar string that's being tuned lower. This cosmological redshift is our primary evidence for the expanding universe, written in the language of light itself. A photon that left a distant galaxy as blue light might arrive at Earth as infrared radiation, its wavelength stretched by the expansion of space during its billion-year journey. But perhaps most mysterious of all are the quantum properties of space itself. According to quantum field theory, what we think of as empty space is actually seething with activity. Virtual particles constantly pop into existence and annihilate each other in timescales so brief they seem to violate the conservation of energy, yet they collectively create what physicists call the quantum vacuum. These quantum fluctuations, invisible and unmeasurable directly, may have played a crucial role in the very formation of the universe's structure. Their tiny ripples amplified by cosmic inflation into the seeds that would become galaxies. Light traveling through this quantum foam experiences effects so subtle, they're at the very edge of our ability to detect. The speed of light in vacuum, that fundamental constant of physics, might actually vary slightly depending on the energy of the photons and the quantum structure of space itself. These variations, if they exist, would be incredibly small, but across the vast distances and timescales of the universe, they might accumulate into detectable effects. The polarization of light, the orientation of its electromagnetic waves, also carries information about its journey through space. As light passes through regions with magnetic fields, its polarization can rotate, much like how polarized sunglasses can reduce glare by filtering light waves aligned in certain directions. By studying the polarization of light from distant galaxies and quasars, astronomers can map the magnetic field structure of intergalactic space, revealing a universe crisscrossed with invisible magnetic highways. Even the quantum entanglement that connects particles across vast distances plays a role in how we understand light's journey through space. When photons become entangled, measuring the properties of one instantly affects its partner, regardless of the distance between them. This spooky action at a distance, as Einstein called it, suggests that space itself might be woven together by quantum correlations in ways we're only beginning to comprehend. The cosmic microwave background radiation, that ancient afterglow of the Big Bang, provides us with our most pristine view of light's journey through space. These photons have been traveling for over 13 billion years, carrying with them the imprint of the universe when it was only 380,000 years old. As they've journeyed through space, they've been subtly influenced by every gravitational field they've encountered, every cosmic structure they've passed through, creating tiny temperature variations that we can measure with extraordinary precision. These temperature fluctuations in the cosmic microwave background reveal the seeds of cosmic structure, the quantum fluctuations that would eventually grow into galaxies and clusters of galaxies. The light itself becomes a time machine, showing us not just what the early universe looked like, but how the very fabric of space was structured in those primordial moments. As we develop more sensitive instruments and more sophisticated theories, we're discovering that the journey of light through space is far richer and more complex than we ever imagined. Each photon is not just a particle or wave traveling through empty void, but an active participant in the cosmic drama, shaped by and shaping the universe through which it passes. The space through which light travels is alive with invisible currents, quantum whispers, and gravitational symphonies. It's a medium that connects every corner of the universe in a vast web of influence and information. And as we learn to read the subtle signatures that light carries from its cosmic journeys, we're not just studying the universe, we're participating in its ongoing conversation, one photon at a time. So tonight, as you rest beneath the stars, remember that every twinkle of starlight has journeyed through this invisible landscape, carrying with it the story not just of its stellar birthright, but of every cosmic cloud, magnetic field, and quantum fluctuation it encountered along the way. The journey of light through space is far more complex and wondrous than we might imagine at first glance. We've explored how photons carry the intricate stories of distant stars, how they bend through gravitational fields, and how they reveal the expanding nature of our universe. But as we drift deeper into this cosmic tale, we encounter phenomena that challenge our very understanding of reality itself. Light doesn't simply travel in straight lines through empty space. The quantum vacuum, that seemingly empty theater between stars, is actually alive with activity. Virtual particle pairs constantly pop into existence and disappear again, creating subtle fluctuations that can influence the path of light. These quantum foam bubbles, as some physicists call them, exist for the briefest of moments, but their collective effect creates a kind of cosmic static that whispers through every beam of starlight. When light encounters magnetic fields in space, something beautiful happens. The polarization of light, the direction in which its electric field oscillates, can be twisted and rotated by these invisible magnetic threads. Pulsars, those spinning lighthouses of the cosmos, create beams of polarized light that sweep across space like cosmic searchlights. As this light travels through the magnetized plasma between stars, it carries with it a record of every magnetic field it has encountered, like a traveler collecting stamps in a passport. This magnetic memory in light has allowed us to map the invisible architecture of our galaxy. We can trace the spiral arms of the Milky Way, not just by the stars we see, but by the magnetic highways that guide cosmic rays and shape the very fabric of space itself. It's as if light becomes a cosmic archaeologist, preserving evidence of magnetic structures that would otherwise remain completely hidden from our view. But perhaps most mysteriously, light seems to dance with time itself in ways that quantum mechanics suggests are far stranger than we ever imagined. In the quantum realm, particles of light can become entangled, sharing a connection that transcends space and time. When two photons are entangled, measuring the properties of one instantly affects the other, no matter how far apart they are. This isn't science fiction. It's been demonstrated countless times in laboratories around the world. Einstein famously called this spooky action at a distance, and it troubled him deeply. How could information appear to travel faster than light itself? The answer seems to be that entangled particles don't need to send information at all. They exist in a shared quantum state, a kind of cosmic dance where both partners move in perfect synchronization even when separated by vast distances. This quantum entanglement might play a role in the very structure of space-time itself. Some theoretical physicists suggest that the fabric of reality is woven from quantum entanglement, that space and time emerge from the intricate dance of entangled particles. If this is true, then every photon of light that reaches us from distant stars is part of an enormous quantum tapestry that connects everything in the universe. Light also carries with it the signatures of the fundamental constants of nature. The fine structure constant, which determines how strongly light interacts with matter, appears to be the same everywhere we look in the universe. But some observations hint that this might not have always been the case. Light from the most distant quasars, carrying messages from when the universe was young, suggests that the fundamental laws of physics might have been slightly different billions of years ago. This possibility sends ripples through our understanding of reality. If the constants of nature can change over cosmic time, it means the universe is not just expanding and evolving in structure, but potentially evolving in its very physical laws. Light becomes a time capsule, preserving evidence of how the universe has changed not just in content, but in its deepest nature. The cosmic microwave background, that faint afterglow of the Big Bang, carries perhaps the most precious information of all. This ancient light has been traveling for nearly 14 billion years, and it bears the imprint of the very first moments when the universe became transparent. Tiny fluctuations in this background radiation, variations of just a few parts in a million, represent the seeds from which all cosmic structure grew. But hidden within this ancient light are even subtler signatures. Gravitational waves, ripples in space-time itself, can leave their mark on the polarization of the cosmic microwave background. These primordial gravitational waves, if they exist, would be echoes of cosmic inflation, that moment of exponential expansion in the universe's first fraction of a second. Light thus becomes our window not just into the visible universe, but into the very moment of cosmic birth. As we peer deeper into space with ever more sophisticated telescopes, we're beginning to see light that has been traveling for so long that it shows us the universe when it was barely a child. The James Webb Space Telescope can now observe galaxies that formed when the universe was less than 1 billion years old. This ancient light has been stretched by the expansion of space itself, shifted into the infrared part of the spectrum by the time it reaches us. But this redshift tells us more than just the age and distance of these ancient galaxies. It provides a detailed map of how the universe has expanded over cosmic time. By measuring the redshift of thousands of distant objects, astronomers have discovered that the expansion of the universe is actually accelerating, driven by the mysterious dark energy that makes up most of the cosmos. Light becomes our cosmic speedometer, measuring the very acceleration of reality itself. Even more remarkably, light allows us to study the chemistry of the early universe. The spectral lines in starlight from the most distant galaxies show us which elements were present in the first generations of stars. We can see how the universe gradually enriched itself with heavy elements, forged in the nuclear furnaces of stars and scattered by supernovas. Each photon carries within its spectrum a detailed recipe of cosmic chemistry, documenting the universe's journey from simple hydrogen and helium to the complex mix of elements that makes planets and life possible. The study of light has also revealed one of the universe's most profound mysteries: dark matter. This invisible substance, which outweighs ordinary matter by 5 to 1, makes its presence known only through its gravitational effects on light. When light from distant galaxies passes through clusters of dark matter, it gets bent and distorted, creating cosmic mirages called gravitational lenses. These lenses allow us to map the distribution of dark matter throughout the universe, revealing a vast cosmic web of invisible scaffolding upon which all visible structure hangs. Some of the most beautiful examples of gravitational lensing create Einstein rings, perfect circles of light where a distant galaxy is perfectly aligned behind a massive dark matter halo. These cosmic jewelry pieces are more than just pretty pictures. They're precision instruments that allow us to weigh the invisible universe and map its hidden architecture. Light also reveals the dynamic nature of space itself through phenomena like time dilation and length contraction. When we observe light from objects moving at high speeds or in strong gravitational fields, we see the effects of relativity played out on cosmic scales. Pulsars, with their incredibly precise timing, become natural laboratories for testing Einstein's theories under extreme conditions. The light from these cosmic clocks confirms that time really does slow down in strong gravitational fields, and that space and time are intimately connected in ways that our everyday experience cannot reveal. As our technology advances, we're developing new ways to listen to the universe's light. Interferometry allows us to combine light from multiple telescopes, creating virtual instruments larger than Earth itself. These techniques have allowed us to image the shadow of black holes, to detect the wobble of stars caused by orbiting planets, and to measure the shapes of distant galaxies with unprecedented precision. Soon, we may be able to analyze the atmospheric composition of potentially habitable exoplanets by studying how their parent star's light filters through their atmospheres during transits. Light may thus become our first messenger from another living world, carrying in its spectrum the signatures of oxygen, water vapor, and perhaps even more complex molecules that hint at biological processes. The future holds even more remarkable possibilities. Quantum communication using entangled photons may allow us to create unhackable communication networks. Quantum computing relies on the strange properties of light to perform calculations that would be impossible with classical computers. And our growing understanding of how light interacts with exotic forms of matter may eventually lead to technologies we can barely imagine today. Perhaps most profoundly, light connects us to the cosmos in ways both physical and spiritual. Every photon that enters your eye has traveled across vast distances and immense spans of time to reach you. The light from the nearest stars is years old, carrying information from the past. The sunlight warming your face left the sun's surface 8 minutes ago, but the energy that created it was generated in nuclear reactions in the sun's core hundreds of thousands of years ago, slowly working its way outward through the dense stellar interior. When you look up at the night sky, you're not just seeing stars, you're seeing across time itself. You're connected to the cosmos through an unbroken chain of photons that stretches back to the very beginning of time. In a very real sense, you are made of starlight, atoms forged in stellar furnaces and scattered across the galaxy by ancient supernovas, now temporarily assembled into the pattern that is you, briefly conscious and aware of the cosmic dance of which you are part. Light is more than illumination, more than electromagnetic radiation traveling at 300,000 kilometers per second. It is the universe's way of telling its story, of connecting every part to every other part, of binding together space and time into a coherent, evolving whole. We've ventured through the cosmos, traced the birth of galaxies from primordial darkness, and watched as gravity, dark matter, and supermassive black holes sculpted the universe into the magnificent tapestry we see today. We've witnessed the dance of collisions, the poetry of spiral arms, and the quiet majesty of elliptical giants drifting through space. But now, as our cosmic journey draws toward its close, there's one final mystery waiting in the shadows, one that may hold the key to everything we've discovered and everything we've yet to understand. You see, for all our telescopes and equations, for all our careful observations of distant galaxies and ancient light, we've come to realize that the universe we can see, the stars and gas and glowing nebulae, represents only a tiny fraction of what's actually out there. The visible universe, everything that shines and sparkles and captures our imagination, makes up less than 5% of the total cosmic inventory. 5%. The rest, the overwhelming majority of reality, remains hidden from our eyes, detectable only through its gravitational fingerprints and the subtle ways it shapes the cosmos around us. This invisible realm is divided into two great mysteries. The first is dark matter, that ghostly substance we've encountered throughout our journey. It doesn't emit light, it doesn't absorb light, it doesn't interact with ordinary matter in any way we can directly observe. And yet it outweighs all the visible matter in the universe by a factor of 5 to 1. Every galaxy we've admired, including our own Milky Way, sits nestled within a vast halo of dark matter, like a glowing jellyfish suspended in an invisible ocean. Without dark matter, galaxies as we know them simply couldn't exist. The outer stars would fly off into space, spiral arms would unravel, and the beautiful cosmic structures we've traced from the early universe to today would never have formed in the first place. Dark matter is the scaffolding upon which everything else is built, the hidden framework that holds the cosmic architecture together. We know it's there because we can see its effects, the way galaxies rotate, the way light bends around massive clusters, the patterns of structure formation that stretch back to the cosmic microwave background. But knowing it exists and understanding what it is are two very different things. Despite decades of searching, we still don't know what dark matter is made of. The leading theories suggest it might be composed of exotic particles that interact only through gravity, relics from the earliest moments after the Big Bang. These particles would be streaming through your body right now, billions of them every second, without you feeling a thing. They're like cosmic ghosts, present everywhere but touching nothing, shaping the universe from the shadows. Then there's the second mystery, even stranger and more profound. In the late 1990s, astronomers studying distant supernovae made a discovery that shook cosmology to its core. They expected to find that the expansion of the universe was slowing down, gradually decelerating under the gravitational pull of all that matter and dark matter. Instead, they found the opposite. The expansion isn't slowing down, it's speeding up, accelerating at an ever-increasing rate. This acceleration requires a kind of anti-gravity, a repulsive force that pushes space itself apart. We call it dark energy, though that name tells us nothing about what it actually is. Dark energy appears to make up about 70% of the universe, dominating everything else combined. It's as if the cosmos is filled with an invisible field that grows stronger as space expands, pushing galaxies away from each other with increasing force. The implications are staggering. In a universe dominated by dark energy, the future looks very different from the past. Galaxies not gravitationally bound to our local group will eventually disappear from view, their light stretched to wavelengths we can no longer detect. The night sky will grow dimmer and lonelier. New stars will still form for a while, but as galaxies drift apart and gas is consumed or expelled, star formation will gradually cease. The universe will enter what cosmologists call the heat death, a state of maximum entropy where everything has expanded and cooled to near absolute zero. But that's trillions of years in the future, so far ahead that the word future loses all meaning. For now, dark energy remains as mysterious as dark matter. Is it a property of space itself? A kind of cosmic constant that Einstein once proposed and later called his greatest blunder? Is it a dynamic field that changes over time? Or is it something even stranger? A sign that our understanding of gravity breaks down on the largest scales? The truth is, we don't know. We live in a universe where 95% of everything is invisible to us. detectable only through its effects on the small fraction we can actually see. It's humbling, really. We've mapped the cosmic web, traced the formation of galaxies, and peered back to within a few 100 million years of the Big Bang itself. We've discovered planets around other stars, black holes at galactic centers, and the faint afterglow of creation itself. And yet the vast majority of the cosmos remains a mystery. This isn't a failure of science. It's a reminder of how much wonder still awaits us. Every generation of astronomers has thought they understood the universe, only to discover that reality is stranger and more beautiful than they could have imagined. The invisible universe isn't empty space waiting to be filled with our knowledge. It's a vast ocean of possibility, full of phenomena we haven't yet learned to see, forces we haven't yet learned to detect, stories we haven't yet learned to read. Perhaps dark matter will turn out to be something we can eventually touch and study directly. Perhaps dark energy will reveal itself to be a key that unlocks new physics, new ways of understanding space and time. Or perhaps these mysteries will lead us to revise our most fundamental assumptions about reality itself. The universe has surprised us before, and it will surprise us again. What we do know is this: we are part of something magnificent and mysterious. The atoms in your body were forged in the hearts of ancient stars, but they make up only the tiniest fraction of what's actually out there. You exist at the intersection of the seen and the unseen, the known and the unknown, carried along by forces so subtle and pervasive that we've only just begun to glimpse their true nature. So as you drift towards sleep tonight, remember that you're not just resting on a small planet orbiting an ordinary star. You're floating through an invisible ocean of dark matter, carried by the expansion of space itself, part of a cosmic story that's still being written. The universe holds its secrets close, but it also holds you gently in the vast embrace of everything we know and everything we've yet to discover. The darkness above isn't empty. It's full of mystery, full of possibility, full of wonders we can't yet see, but that shape every moment of our existence. And perhaps that's the most beautiful thing of all, knowing that no matter how much we learn, no matter how far our telescopes can see, the universe will always have more stories to tell, more secrets to whisper to those patient enough to listen. Sweet dreams, fellow traveler. Here is part 12 of the script for The Sleepy Scientist, Starlight and Shadows, How Light Travels Through Space. And so we arrive at the end of our gentle journey through the cosmos, following light as it dances across the universe, carrying stories from the very beginning of time itself. We've watched photons born in the hearts of ancient stars, witnessed them bend around black holes, and marveled as they stretch across billions of years to reach our waiting telescopes. We've seen how light reveals the invisible architecture of reality, the dark matter scaffolding that holds galaxies together, the mysterious dark energy that pushes space itself apart. Light, it turns out, is far more than illumination. It's the universe's messenger, its memory keeper, its most faithful storyteller. Every ray that touches your skin began somewhere else, someone else, carrying with it the fingerprints of its journey through space and time. The starlight falling softly through your window tonight may have witnessed the birth of planets, the collision of galaxies, the quiet death of suns. It has traveled distances so vast, they humble the imagination, all to arrive here, now, in this moment of your evening. We've learned that light behaves as both wave and particle, that it can be twisted, polarized, entangled with its distant siblings in ways that seem to defy logic. We've discovered that it doesn't always travel in straight lines. that massive objects bend its path like valleys channeling streams. We've seen how the expansion of space itself stretches light, redshifting it toward longer wavelengths, creating a cosmic Doppler effect that tells us the universe is growing larger with each passing second. Through gravitational lensing, light becomes a cosmic magnifying glass, allowing us to peer deeper into space and further back in time than should be possible. Ancient galaxies, invisible to our direct gaze, reveal themselves as distorted arcs and rings of light, their images multiplied and magnified by the gravitational fields of intervening matter. It's as if the universe has provided us with natural telescopes, scattered throughout the cosmos, waiting for us to learn how to use them. The cosmic microwave background radiation, that faint afterglow of the Big Bang, bathes everything in the whisper of creation itself. This ancient light, stretched and cooled by billions of years of expansion, carries within its subtle variations the seeds of everything that would follow. Galaxies, stars, planets, life itself, all traced back to tiny fluctuations in the temperature of this primordial glow. We are quite literally surrounded by the light of Genesis, the electromagnetic echo of the moment when space and time began their long dance together. Dark matter and dark energy, those mysterious components that make up most of our universe, reveal themselves only through their effects on light. We cannot see them directly, cannot touch them or trap them in laboratories, but we know they exist because of how they bend starlight, how they influence the cosmic web of matter, how they drive the accelerating expansion of space. Light becomes our detective, gathering clues from the unseen majority of reality. Quantum mechanics adds another layer of wonder to light's story. Photons can become entangled, their fates intertwined across vast distances in ways that Einstein himself found unsettling. They can be polarized, their electromagnetic fields aligned in patterns that encode information about the magnetic fields they've encountered, the dust they've passed through, the very geometry of space itself. At the smallest scales, light reveals the quantized nature of energy, the discrete packets of electromagnetic radiation that power everything from the warmth of sunlight to the complex chemistry of life. Throughout our journey, we've seen how light connects us to the cosmos in the most intimate ways. The calcium in our bones was forged in the nuclear furnaces of massive stars, announced to the universe by the light of supernovae. The iron in our blood carries the signature of stellar death, scattered by explosions so bright they briefly outshine entire galaxies. We are made of star stuff, and it is light that tells us so, carrying the spectroscopic signatures of the elements within us back to their cosmic origins. The story of light is also the story of discovery, of human curiosity reaching across the void to touch the infinite. From Galileo's first telescopic observations to the James Webb Space Telescope's infrared revelations, each advance in our ability to gather and analyze light has opened new chapters in our understanding of the universe. We've learned to see in wavelengths invisible to our eyes, to detect the faintest whispers of radiation from the edge of the observable universe, to measure the subtle wobbles of starlight that reveal distant worlds. And yet, for all we've learned, light continues to surprise us. Fast radio bursts, those mysterious flashes of radio light that appear and vanish in milliseconds, remind us that the universe still holds secrets. Gamma-ray bursts, the most energetic explosions since the Big Bang, pour their light across billions of light years, briefly visible to our instruments before fading back into cosmic darkness. The universe is still writing its story in light, and we are still learning to read its luminous language. Perhaps most remarkably, we've discovered that most of the universe remains hidden from us. The ordinary matter that makes up stars, planets, and galaxies accounts for less than 5% of everything that exists. Dark matter and dark energy, invisible to light and known only through their gravitational effects, comprise the vast majority of reality. We live in a universe where the visible is the exception, where light illuminates only a small fraction of what is. The shadows between the stars are not empty space but filled with mystery, with forms of matter and energy we are only beginning to comprehend. This humbling realization doesn't diminish the wonder of what we can see, but rather amplifies it. Every photon we detect is precious, a rare messenger from the darkness, carrying information from realms we cannot directly access. The light we gather with our telescopes is like finding letters in bottles washed up on a vast, dark shore, each one containing news from distant lands we may never visit, but can explore through the stories light tells us. As you drift towards sleep tonight, remember that you are surrounded by light, bathed in the gentle glow of photons that have traveled unimaginable distances to reach you. The soft light of your bedside lamp began its journey in the sun 8 minutes ago. The glow from distant streetlights carries the signature of human civilization, a pale echo of our presence on this small world. And beyond, invisible to your eyes but detectable to sensitive instruments, the cosmic microwave background continues its eternal whisper, the fading voice of creation itself. The universe speaks to us in light, and we have learned to listen. We have built cathedrals of glass and metal to gather its faint signals, developed mathematical languages to decode its messages, trained our minds to see beyond the visible spectrum into realms of infrared and radio, X-ray and gamma ray. We have become fluent in the dialect of starlight, conversant in the grammar of gravitational lensing, literate in the poetry of cosmic radiation. And still, the greatest mysteries remain just beyond our reach, hidden in the shadows between the light. Dark matter clusters in halos around galaxies, invisible but essential. Dark energy pushes space apart, accelerating the expansion of everything we can see. Quantum fields fluctuate in the vacuum, creating particle pairs that briefly exist before annihilating back into nothingness. The universe is far stranger, far more wonderful than the light alone reveals. This is perhaps the most beautiful aspect of our cosmic journey through light and shadow. For every answer we discover, new questions emerge. For every mystery we solve, deeper puzzles reveal themselves. The universe does not yield its secrets easily, but neither does it hide them completely. It leaves clues in the light, hints in the darkness, invitations to keep exploring, keep wondering, keep reaching toward the infinite. Tonight, as you close your eyes and surrender to sleep, let your mind drift among the stars. Imagine the photons streaming past your window, each one a traveler from some distant sun, each carrying its own small piece of the cosmic story. Picture the invisible dark matter flowing around you like a gentle tide, shaping the very fabric of space without announcing its presence. Feel the subtle push of dark energy, the force that will ultimately determine the fate of everything we know and love. You are part of this story, woven into the cosmic narrative by bonds of light and gravity, chemistry and quantum mechanics. The atoms in your body remember their stellar birthplaces. The light in your eyes carries information from across the universe, and your very existence is proof that matter can organize itself into patterns complex enough to contemplate their own origins. In learning about light, we learn about ourselves, about our place in the vast dance of energy and matter that we call the cosmos. The shadows hold their secrets still. The dark corners of reality remain largely unexplored, and the greatest discoveries may yet lie ahead. But tonight, it's enough to rest in the gentle embrace of starlight, to feel connected to the infinite tapestry of space and time, to know that somewhere out there, light is still traveling, still carrying messages from the edge of everything, still illuminating the magnificent mystery of existence itself. Sleep well, fellow traveler through space and time. The universe will continue its luminous dance while you dream, and when you wake, there will be new light to discover, new shadows to explore, new wonders waiting just beyond the horizon of human understanding. The cosmos is patient, eternal, and infinitely generous with its gifts of light and wonder.